Done.
Okay, great. So it's all yours, Daryl.
Okay,
Right?
share my screen.
We can see it.
Okay. All right, everyone, let's get started. So my name is Daryl. Joining me for this session on 8360 and 8400 VXLAN is Satish, Pramod, and Matt. This is the agenda. We're going to start with the overview. We're going to go through the use cases, and we're going to go through the details, which I'll hand over to Pramod and Satish. And they will also cover the configuration, best practices, troubleshooting, and the resources. Finally, Matt will cover the demo portion of this topic. So overview. In the past, right, in 10.5 and before, 63, 64, 83, 25 supported both VXLAN EVPN, and 8400 only supported EVPN control plane. Right now in 10.6, both the 8360 and 8400 will support both VXLAN and EVPN data plane and control plane. So 8360 is really targeted for core and aggregation layer of campuses, as well as data center, leaf and spine, and compact spine, really, right? Because it's small switch. 8400 can be targeted for campus, data center core, or large-scale border router requirements. Use cases. In the data center, as you can see here, typically we deploy a leaf and spine physical topology. Leaves are in the rack that connects to your servers, the compute nodes, and they're typically VSX, as you can see here. We typically recommend distributed layer 3 gateways with symmetric IRB in the data center. So before 10.6, we had to use the A325 as both compute and border leaf VTAPs. These are the border leaves connecting out of the overlay network to the non-overlay network. Not much choice, A325 only in the past. And in the spine, we could only use the A325 or 8400 if you needed higher port density, because A325 had 32 ports max as the EVPN route reflector spine in the past. So right now with 10.6, there are more options, as you can see now. In the spine, three models, same for the leaves. So you can pick and choose based on the port density, the port types. So especially in the past, right, we had customers who wanted to do lots of copper down to the servers. A325 couldn't do that, so A360 now has that capability. We are now filling that void for copper connectivity in the compute racks with the A360. Of course, the 8400 could also be used like an end of row or middle of row switches that connect to all the other servers within the whole row. So that's another valid option. And distributed gateways, as you can see here, that means the default gateways are the same, and they are spread out on different racks. So same .1 default gateway is on every leaf. That means when the VM vMotions to different racks, there's no need to re-arc. So it's optimized for that. And of course, with distributed default gateways, if VMs need to communicate on different subnets within the same VRF, they can do it locally at the top of rack. So 10.10 and 11.10, if they need to communicate, this leaf will be able to route traffic directly. There's no need to leave for the traffic to leave the leaf switch, right? Get into the physical fabric. So that's why we recommend this distributed layer 3 gateways for the data center. Okay, that's the campus use case. And that's the DC use case. For the campus use case, we also recommend distributed layer 3 gateways for the campus. Before 10.6, we had to use the A325 in the edge data center. Edge data center, typically the campus, they don't have that many racks. So they have an edge data center, and most of the apps are in the cloud. They had to use the A325 in the compute most of the time. And the A325 as a core, or even the 8400 as a core. But now there's more options. If it's a small campus, you could use the A360, right? If it fulfills the port density requirements. But now as well, in the past you could use 8400, but now 8400 can also be used since it supports VXLAN. And the border VTAP now, you can see there are more options. You notice that in the data center, we only recommend 8,000, right? Because it's so critical, right? We do not recommend the 63 or 6400s in the DC or even as the border. Those should be left as access because of the VSF capability, single control plane. That's why we recommend 8,000. Even though the 6400 supports VSX, we still recommend 8,000 in the data center. A360 can also be used as a non-VTAP campus X switch here to connect to the access switches. But there's no need to run VXLAN, right? Just transit. Scale-wise, to give you an idea of the two new switches, right? Things might change, so please refer to the data sheet and TFM after 10.6 goes GA for final confirm numbers. This is what I grabbed early, but most probably it will change. Details-wise. So Pramod, you want to just jump in?
Yeah. Hi, everyone. I'm Pramod from the VXLAN team for 8360. Uh, so here are the scales for it for the 8360 box, which runs the Rosewood family of the ASICs. So we do have the 1024 VTEPs and 255 L3 VNIs and 4093 total VNIs. So that's the scale on the 8360 as far as VXLAN is concerned. So move to the next slide.
Okay. These are the numbers for 8400. It supports about 1 less than 4K VNIs. It supports 1K VTEPs and 255 L3 VNIs. The host scale is 54K over the VXLAN. And yeah, as Daryl mentioned, you need to look at the TFM documentation for final numbers. There are a couple of caveats with 8400 VXLAN implementation. One is the DSCP value on the inner packet or the overlay packet will not be honored on the underlay. So the DSCP will not be copied from the inner to outer. What this means for a customer is the traffic will not be prioritized on the underlay as expected. And this is a feature we are planning to support in the future, so we'll be working on it in the later releases. But right now we have this caveat. And once the packet is decapsulated, the inner DSCP will get applied based on the next stop, based on the router configurations of the switches. So it's only on the underlay the DSCP will not be honored. And on the new 25 gig LCs, which is JL687A, with the enablement of VXLAN, GRE is not supported anymore. This is again something we are making it to work, which will be supported in the later releases. So moving towards the configuration part of it, and it's just kind of guidelines on how these deployments can be taken. The earlier white paper that was published in the Aruba portal for EBP and Symantec still holds true. The CLI commands for 8360 or 8400 has not changed. So pretty much it's all the same. It's just that the feature is enabled on a couple of more platforms right now. The much awaited SVI to and Active Gateway, same IP for SVI and Active Gateway, is actually not supported in 10.6. We are planning to support that in it just slipped through in the later part of the release. So we will support that in the future release, and it's expected sooner. On the best practices, so again, it is all what our best practices are stated in the earlier white paper, they still hold true. For whatever was published for 10.5 still holds true with 8360 and 8400. For 8400, if your host scale is say above 44K, 40K or so, it is better to use route redistribution than host redistribution. So that way it can scale, and 8400 is core box. So if your host scale is above 40K, it's better to use route redistribution. And jumping on to troubleshooting, it is all going to be the same. These are just guidelines, and I'm just going to walk you through really quickly here. So if you look at this, for example, if you are asked to debug a problem where you say, okay, my traffic on VXLAN tunnel is not working, right? that's a very high level statement. So a quick step or a quick stab at it is to look at show interface VXLAN VTEPs, which will show the operational status of the tunnel. And if your tunnel is operational, then you can jump on to next bullet item. If it is not, then you can go into the sub bullets and see what really is going wrong. So on a VXLAN tunnel, one thing could be that your underlay is broken, your EVPN communication is broken, or there is some misconfiguration in the spine or the remote VTEP. So those are the steps listed here to check on the underlay whether the show BGP all VRF all summary command, which will show the peer establishment in BGP. If you're using the OSPF as your underlay, there should be an equivalent command, which I have not listed here, but yeah, I think you would get the sense of it. So it's basically looking at whether the BGP peers or OSPF neighbors are established in the protocol. The second thing to check is whether the EVPN on the current VTEP is advertising that it's the L2 VPN details. And same thing is whether the spine is configured correctly or not for redistribution of EVPN, which you can use the same command on the spine. And you can walk through on to the remote VTEP to say, okay, if that's configured correctly or not. So that's one thing. So if for example, if the tunnels were operational, then the next thing to check if the VNI is operational, and the command for that is show interface VXLAN VNI. And if that's not operational, again, the same steps like show BGP L2 VPN EVPN to see if the routes are, the L2 VPN is advertised correctly or not, and then hopping onto the spine and to the, one step at a time towards a VTEP, remote VTEP, to make sure the configuration is all done correctly across the endpoints. If your use case is more like, okay, I have VXLAN tunnel operational, but some of the host is not working as expected, some of the routes are not happening correctly, right? If it boils down to that, then it's the show IP route BGP all VRFs, which will show all the EVPN routes plus all other underlay routes as well. There may be options to trim it to just to EVPN of your interest and kind of print that. So you could also check whether you're redistributing host or route. And you can also check the show BGP L2 VPN, EVPN to see the particular VNI is getting advertised or not. And so the other thing is, if it all looks good, there is this show ARP all VRF and show IP neighbors, IPv6 neighbors all VRFs to check if the neighbors or the host that you are of your interest is learned or not. This probably will give you a broader output. You can always do a pipe include to look and grab for your specific entries of your interest. Okay. Moving on. So these are commands very specific to 8400. For example, this is the diag dump VXLAN basic, or if you have a support file from a customer, this is the file path feature VXLAN diag dump.txt in the support file tarball. Those commands would give the VXLAN output PI information. When I say PI, that's going to be the same format, same data for across all platforms. So that will be contained in that. And the difference between the show commands and this output is this is more from the layer below the show outputs. And typically show outputs come from these data as well or from the DB. But this is more of a one level layer down below the DB. And the next one is the VXLAN platform, 8400 platform information, which is more towards the ASIC. And we also have internal logic counters, that error counters that we maintain from the software side. And these are not the interface counters that you see usually packets, RxTX counters. These are not that. These are more internal logic counters. And all these are available on this file or when you run this command. To get to the diag dump, you need to run diagnostics enable, and then you would see this command. So if for folks, if you're not aware. The same thing, this is from the MM or the management module. There is also a line card level support file that will be available in the support tarball, and it will be under in the LC star.tg tarball. So it will be the diagdump VXLAN.txt is the file name, and you can also generate that on a CLI using this command. So this again has information from the, and these all are PD specific. There is nothing common across platforms on this one. So this will have LC level information and the ASIC level information. So we should, in dev would need this data when you have an issue. So that's why we usually ask for support files, and these are all part of these support files. Again, it has the counters. This counters is the logical counters from the LC. So these two are different, whatever you saw in the MM and on the LC. And it has multiple categorization, like errors, warnings, info, and debug. So you would need that. And remember, mostly once the tunnel is up, there is VXLAN is only a transport medium. So pretty much any host or any routes that is coming, that is getting routed onto this VXLAN is not actually directly dependent on VXLAN. It's all the other features that has to point to the tunnel. So for example, if you have an issue with a host that's not communicating on the tunnel, or if you have a route that's not going over the tunnel as expected, then it's just not the VXLAN. It's other features that has to come into play. Example, EVPN, L3PD, L2. So pretty much, if you need to look at the guidelines for the L3PD or L3 programming and debugging to look at any problems that if the tunnel is up and the tunnel is working as expected for some of the host or some of the traffic, and if the traffic is partially dropped, then you need to look at other entities like, as I said, neighbor discovery, L3, and EVPN. So you may have to refer multiple those debugging documentation for taking a stab at it. I'm not listing all of them here, just on context here. There is also VXLAN counters in the 8400 box, and the little difference is there is an command to enable aggregate counters in other platforms. In 8400, the counters are enabled by default, and here is the command. I'll show you the sample command outputs on the next slides, and we can talk about it more. Here is the command. There is no enable disable that's needed on 8400 platform. Okay, moving on to the next slide. So this is, I'm not putting all the content of the diagdump output in this slide, but just a sample of it. So if you look at it here, the VPN information is available from the MM on the diagdump output. Here is the VPN ID that's configured on CLI. This is the VNI ID that is present, and this is the VRF. VRF name, VRF internal ID, the VLAN associated with the VNIs, and the multicast IDs for the flood groups, and whether it's an L3 VNI or not, or it's a symmetric or asymmetric VNI. So the last one is the symmetric VNI, and this is more internal. HA state is more of an internal. So diagdump LC, same thing on the same cache, VPN cache is what you see. So when you see the data is consistent between MM and LC, then you're all good. So just in case if you have to ever look at the diagdump output of support files, then you can always compare this data. The first level of data from the diagdump and the diagdump on MM and LC should be the same. There may be extra columns that you could ignore, but the base data should be the same. And the bottom data is actually from the ASIC itself. And this data might be smaller than what you would see for the same comparison with the LC. This LC ASIC output is also part of the diagdump LC. And if you look at it, the hardware just needs this information, just the VPN ID and the VNI ID, and they will map. So this kind of a mapping that if you have to ever look at a diagdump output, you can pretty much look through these IDs and see if they're consistent, they are good. So this is just a simple example of one particular object in the diagdump output for VXLAN. And here's the sample output of show int VXLAN 1 statistics, which is the interface counters. So it gives the interface name VXLAN, and it's always going to be the same. The RX bytes, RX packets, for because of the width reasons, they're like multiple lines here. So 9015 is the RX packets, and this is a drop counter, TX bytes and TX packets. So pretty much you will always see, we don't support RX broadcast on 8400. So pretty much you will see TX and RX bytes and packets that's counted here. And by the way, if there is next stops coming in and going away, the counters will kind of will lose the counts for the next stops that's not part of the tunnel anymore. So that's on the underlay. If there are underlay changes, these tunnels would get retuned a bit. There may be a loss of values there. So you could use clear interface VXLAN statistics, and if you want to clear and then just take a quick note on how much packets are going, then you can use clear. That will be handy for you. And having said that, Pramod, do you want to share? You want to take it from me?
Yeah. Thanks.
Let me stop sharing.
All of you can see the screen.
Yeah, we can.
Okay, so coming to VXLAN 8360, so we have the same commands similar to 8400. So similar to 8400, that's the show command, show interface VXLAN, show interface VXLAN VTEPs, VNI, and the statistics. So these commands remain the same to display the VXLAN information on the box. So the VXLAN information would be in the support files. So that's again like this after you enter the support files for the switch, right? So it would be under feature VXLAN diagram, or if you want to display it in the CLI, so the command to display the diagnostic information for VXLAN would be diagram VXLAN basic. The information that would be shown here would be the VXLAN information that's programmed on the and as well as on the line card. So it's split into three parts. So the plugin cache, the agent cache, and the ASIC. So the plugin cache and the agent cache are mainly the software caches of what is programmed by EVPN and by the CLI. So you would be seeing those dumps under the various keywords, plugin cache dump, agent cache dump, and the ASIC dump begin in this particular VXLAN diagram command. Also, so as Satish did mention that if your tunnels are up, but you are having your host entries or the IP routes which are not which are pointing to the tunnel, so those information can be if you want to find out any LCPD debugging. So those are captured in this particular wiki link for your reference. So here is a sample display of the diagnostics information for VXLAN. So here is plugin cache dump is mainly on the So this is nothing but your VNIs here, which are programmed in the CLI, and these are the internal rep groups that are used for the VNIs. And if you see here, the VNI 10, which would be associated with VLAN 200 and 10 associated with 100. So those are the L2 VNIs. So this is an L3 VNI. Okay. So the next part that is there in the display is the tunnel and the tunnel information, what are the source IP and the destination IP of the tunnel, and also the underlay information for the tunnel. So what is the next stop information, what is the next underlay information are all captured in this particular display here on the plugin cache. The next would be the NetVP cache. So the NetVP, what VNI is associated with which tunnel. So as you see here, so there is a tunnel index associated with each and every tunnel here. So which particular VNIs are associated with which of these tunnels are captured here. So you could see both the VNIs are being associated with the tunnel ID 1 here. So next, moving to the agent cache here. So this is on the line card. So the software cache of the VXLAN objects on the line card. So it's again, you could do a comparison of what is there on the and as well as on the LC. So we have the VNIs and their respective replication groups that are there. So this is more of an internal implementation for the VPNs, for the VNIs. And again, you have the tunnel information. So what is the source IP, destination IP, and also the underlay information that's there, which particular next stop is being used, and what's the port on which the NCAP and the DCAP traffic has to go out and come in. So that's the next hop information that is captured here. And again, you have the net VP information, that means which tunnel is which particular VNI is associated with the tunnel. So that information is captured here. So this is mostly the cache information on the line card. So moving forward, so now we get to the ASIC dump. So we have the VPN information and associated with which particular replication groups. And then we have the tunnel entry and tunnel exit. So tunnel entry, we mean by the packets entering the tunnel and how they get encapsulated out, and tunnel exit is how they exit the tunnel, and which means the decapsulation process. So we do see the status of the tunnels, and as well as we do see the counters, that's the encapsulation counters and the decapsulation counters here. And what is the underlay here? So we see the underlay information, that's the MAC, and as well as some internal information which dev would be needing in case of there is any problem here. So this is mainly the tunnel information as far as VXLAN is concerned on 8360. And this is nothing but again the net VP, as I told you before. So which particular tunnel, which particular VNI is associated with the tunnel. So these are these are the main information that would be needed on 8360 VXLAN to debug any issues. Okay, Vital, you want to take this slide up?
All right. Hello, everyone. My name is Matt Finlay. I'm with the 8400 VXLAN PD team as well. So just to kind of just go over a short demo that shows the functionality of an actual VXLAN deployment. We have a distributed L3 gateway set up. On one side, we have an 8400 VSX pair. And on the other side, we have an 8360 VSX pair. Connected through two spines that are just 8325s that are not configured in VSX or VXLAN in any form or fashion, just doing the routing. And then on the southbound end, we just have a couple servers that are enabled that we're just going to show some connectivity through. All right, and then just to kind of give another key point here, for each one of these subnets that the VMs are connected to, we have 10, the third octet is the VLAN, the access VLAN on that side. So you'll see that we'll have VLAN 10 and 11 underneath the 8400, and then we'll have VLANs 10 and 12 underneath the 8360. All right, so let's go to the server and the switches. So this Leaf 1A here is the 8400 VSX pair. It's the primary node. So everything's been configured. You know, we can look at the running configuration and see that we have 2 VLANs configured on the system with 3 VPN. And then you'll see all the typical configuration stuff. Let's get to the VXLAN towards the bottom here. So our source IP is 11.3, which is our loopback address. And then we're connecting VNI 10010 and then 100001 for our L3. This will be an L2 VNI. And then we have the BGP OSPF configurations below that. So everything's configured through EVPN, so it's all just automatically shows up. The first thing you want to do when testing your deployment is verify your VXLAN configuration. So if you guys were paying attention during the presentation portion, we remember that it's show in VXLAN VTEPs. And you can see that these are EVPN VXLAN endpoints, as well as everything's in the operational state. Again, if operational is not shown here, if you see configuration error or activating, it means you have an issue somewhere, either in your underlay or your configuration of your overlay. So you'll need to dig in and kind of see what's going wrong. But again, we see here that this is our VNI for our L2 VNI. So, and then this will be our L3 VNI, which is our routed VNI. So let's go ahead and just do a simple ping test to begin. So what we'll do here is, so this node here is configured as 10.1.10.10. So he's underneath the 8400, and then we're going to ping the same L2 VNI on the other side attached to the 8360, and that IP address was 10.1.10.11. And you can see the connectivity is there. One additional step that I've done is to add L2. I've added some sniffers to both spines. Since we have multiple spines, I had to connect to both just so we could see the packet stream through the fabric. So let's just go see. So this is spine 1, and we can see here, I'll just stop. We can see this VXLAN packet traversing through. So this is out of the 8400 into the spine, and we see this is the echo request. So we see our source IP and dest IP of the tunnel. And then you see the VNI here, which you could get your hex calculator out, but I promise you that it's 1000 or 10010, which is our L2 VNI. And then the inner IP being 10, and then we're pinging 11 echo request. And if we let this go, I only see echo requests. So that tells me that the reply is coming through spine 2. So let's come to the spine 2 real quick. And we can see that here's the echo reply again. So now the source and dest are reversed. It's the same VNI, and we see the source and dest are reversed on the inner payload. So everything is working as we would expect for L2 VNI packet. A couple other things just to look at or to take note of. Let's look at counters. So showing VXLAN, we can see that we have decap here and cap here. Those are our current statistics. If we run it again after more packets have traversed through the fabric, we don't, that means they're probably going to the secondary. Apologize, let's go to the other side. Since we have multiple VSX hosts, they could be going either direction. So we'll see that, and then showing VXLAN. And our packets are not incrementing. So let's just leave that for now. Same values. Yeah, these are, yeah, so they're incrementing here. We need to look at that. The aggregate statistics are not incrementing as expected, but we see the values on showing VXLAN statistics incrementing. So everything looks good there. A couple other things to look at for L2 VNI. You will see that the MAC addresses are learned across the fabric. That's one of the inefficiencies of L2 VNI, is that you have to have MAC and ARP entries across all hosts that are connected, so on both sides. Whereas when you use some symmetric or L3 VNI, you won't see these, and you don't need to have all the resources used up on those entries. So you can see this L2 VNI. If we went and looked at the one interface of that host that we're pinging, we would see that that's his MAC address. And then if we do show ARP, and then we're connected through VRF1 in this configuration, show ARP, VRF1, we can see that the ARP is learned also over VRF1 over the VXLAN interface. All right, and then quickly, let's ping the L3 VNI. So that is, so from our 10 address, which is under VLAN 10, we're going to ping 10.1.12.10. You can see our pings are working. Let's go back to our sniffer and look at these packets. So here's the echo reply. We see the VNI is now changed. All the other information is going to be the same on the outer portion because the VTEP is the same. We see the VNI is changed, and again, this is 100001. If you could decode that, and then we see our source IP on the destination is 10, and then 12. So this is the echo reply. And then if we scroll up, the echo requests are also coming through. So everything's traversing through the same switch. And just a couple other key components here. We did show in VXLAN VTEPs. Another good command for verifying the fabric is show BGP, L2 VPN, EVPN. And you can see our you can see all of the L2 VNIs configured, which hosts they're connected to. So both ends of the VTEP. And then you can also see the L3 VNIs if you scroll further down. So it just further proves the connectivity and what's connected and what's not. And then just finally, the diag dump command that we discussed earlier. So if you enable diagnostics and then do diag dump VXLAN basic, this will give you all the PD information that was kind of described in the slides, but it's a very good command to know and be helpful to use in your triaging and such. And that is all I had for the demo. So thank you very much. If there's any questions, feel free to, I'll turn it back to you, Daryl, and then.
Sure. There's a question. So are the VXLAN statistics commands available on all platforms now?
So they should be available on all platforms. The difference with 8400 is you don't need to do anything explicitly to enable those statistics. For the 8325 and 8360, I believe you have, or for 8325, definitely you have to actually enable aggregate counters for VXLAN. Pramod, I don't know if you can speak to 8360.
Yeah, 8360 also the statistics are available on the command by using the command show interface VXLAN statistics now. Yeah, it's available.